Okay, so I'm going to tell you a bit about high energy physics that takes place in CERN. Okay, now CERN is a French word that stands really for the Center for European Nuclear Research, but really we don't do nuclear research, we do particle physics. And there are some groups here at Northwestern that are heavily involved in the research done well, this is actually in Geneva, Switzerland. So the idea behind the accelerator there is that you have a gigantic ring, okay, which is actually underground, and the ring is 27 kilometers around, so it's really gigantic. I mean, you could put it around Chicago. What we do is we put protons in the machine that circulate in one direction, and then they also circulate in the other direction at the same time. And the path that they take in this ring only intersects at 4 distinct places. Okay, for example, you can imagine that they intersect here, and yet you get collisions at that point. In fact, as I said, there are 4 places where they collide. Now, at each one of these places where they collide, we put a gigantic experimental apparatus. I mean, they have funny names. For example, this one over here is called Atlas. This one over here is called Alice. And then this one has the boring name of LHC-B. Okay? The one that's over here that's by itself is my experiment, CMS, and that stands for compact muon solenoid. And I can tell you what those words mean in a minute. Okay, so I've drawn this as a little circle here as if, you know, it fits in this office, but given that the ring is 27 kilometers around, you could imagine that also where we have these experiments are gigantic. All right, so the CMS experiment is basically 3 stories tall. All right, you can compare it to like Hubble Space Telescope, stuff like that. So what happens? You asked me what happens when these protons collide. Well, if you remember a little bit about your chemistry, if you think of what a hydrogen atom is, hydrogen atom has a proton in the middle and an electron that's whizzing around in an orbit, okay? Now, the proton is pretty big compared to the electron, and if you look inside the proton, you'll find that there are 3 things inside of that, and we call those quarks, okay? So if you imagine now that we have 2 of these protons coming together and smashing at a very, very high energy, what happens is that these quarks, like this one, and over here might be an anti-quark, they annihilate and give you momentarily pure energy at the point where they annihilate. And because we've got, from Einstein's equation, the fact that if you have a lot of energy, that's equivalent to a lot of mass, what we can do when we have these little quarks annihilating, giving us a lot of energy, is we could produce something that's very heavy. Okay? So one of the things we can produce is different kinds of quarks. I mean, to give you a little bit more background, the proton has 3 quarks in it of 2 different kinds. We have an up quark, and an up quark, and a down quark. Now, those sound like really silly names, and they are really silly names, but those are the building blocks of matter, and okay, that's what we call them. And in nature, in this room, in the universe, you really only find up quarks and down quarks and nothing else. But there are other kinds of quarks that you can produce. There's the strange quark, so if we can make a little table here. There's the up and down quark, there's the strange quark, and the charm quark, and then there's even the top quark and the bottom quark. Now, if you think about this proton here, it has a certain mass. This top quark here, which is the heaviest of them all, is actually 280 times heavier. Now, the proton's kind of big, all right? This is about 10 to the minus 15 meters big. That's pretty small. But for us, that's really big. But these quarks inside, they have absolutely no size at all. Okay, these quarks are just pure points. You know, like in geometry, when you do geometry, you talk about lines and points. This is really a point. You cannot measure how big it is. It has no size whatsoever, okay? So these up and down quarks that are inside the proton have very little mass, but this top quark up here is, as I said, about 270 times the mass of the proton. And so if we want to produce these top quarks, then these protons have to collide at a high energy. So in order to look at things that are heavier than this top quark that we know about already, we need more energetic beams. The ones that were at the tevatron, okay, were 2 TeV. Okay, and so that's about 2,000 times the mass of the proton, according to Einstein's equation here. But this one at the Large Hadron Collider at CERN, that will be 14 TeV. Now that's the ultimate energy. What we did this morning was to run at 7 TeV. And the reason we ran it as lower energy is because there are 2,000 superconducting magnets around here, and we don't want to go for broke in the beginning. We want to be a little bit cautious. We know that some of the magnets are likely to misbehave if we try to go to 14 TeV. So we're going to 7 TeV, and we'll run that way through 2010 and 2011, and then go to 14 TeV in 2012. Okay? All right.